In this video, we're going to look at higher performance in SQL. So we're going to look at some of the issues that enhance performance, whether they be from changing the queries, rearranging those, or using index or some other mechanism. We want to have the highest performing and fastest queries possible. Let's take a look at several areas of performance improvements that you can get in SQL Server. First, in the SQL Server installation, among other things, make sure that you keep the data and the log files separate. There are many choices in your installation, and being strategic about those choices is important. The second area is locating the problems if the system is slow. There are a lot of different areas. Some of those can be related to a query. Some of those can be related to hardware, software setup, or the data connections. So it's important to locate what those problems are. Next, you need to find the worst performing queries and see if you can rewrite, fine-tune, do something about those poorly performing queries. Next is to build an execution plan for complex queries, and once you get a really good execution plan, then reuse it. Now sometimes people will optimize a query but not save the execution plan, and the system has to come up with that new each time. The next area is adding indexes where appropriate. So you look at specific columns or combination of columns that could improve a query's performance, and perhaps an index is appropriate. With that, sometimes it's important to remove redundant or poorly performing indexes. So we're going to look at these areas and find some specific things that you can do to increase performance. The first thing we look at with performance here will be some rules in queries that we want to follow and obey that we generally know are best to follow. First, do not use an or condition in the from clause when you perform a join. So take, for example, down here we have an or clause, and we're saying where trade date is equal to actual date, or year of trade date is equal to year number in the calendar table. As I'll show you in a minute when we see the execution of the query, that does a tremendous amount of acquiring and using and storing resources. Second, don't use a function on the left side of the comparison. So where we did year here, that's easy to write and it's fast to write, but it's slow in executing because it needs to make that comparison then for every row. Also, don't do a select star. Instead, list the columns for faster execution times. So let's go ahead and execute that query. We'll point out a few things here. First, I want to look at the execution plan. So I go to Query and include actual execution plan. Next, I set statistics time on. I set statistics IO on so I can get some statistics. Now I had to modify the query a bit that was on the previous slide because I couldn't get it to run on a pretty powerful server. So I modified it only to look for ticker symbol equal to Apple. Even still, I'll hit execute, it'll run, but let's go where it already did run. And we'll notice a few things here. Almost 3 million reads, logical reads, and it was very slow. It turned out, we'll look at the bottom here, to take 1 minute and 11 seconds, as we see over here in the bottom right hand corner. And even though there's only 400,000 rows in stock data and 50,000 in calendar, because it had to go through it so many times, it reads some more than 1.8 million rows. So that turned out to be a really slow way to do it. We see that this is a very slow, poorly performing query but it's amazing how poorly performing it is. Again, it shows that there's more rows affected than we have in both tables combined by a long ways. If we go here to the execution plan, it's hard to think of a worse execution plan. So we do nested loops interjoin as one of the steps here in our execution plan, and that's one of the slowest steps. Then we do a clustered index scan here. We do another one here. So many of these operations we're actually having to do more than once. And notice how many of these exceed 100% of the cost. So this is far and exceeds 100%. So that's a very slow, poorly performing version of the query. So let's take another version of this query and see if we can't speed it up. First, we'll take the OR clause out because it doesn't actually help us get the answer. And even if it did, we'd put it in the where clause. So let's take this OR, and notice that we'll also take the year of trade date. So you don't want to have a function there that is on the left side of the equal sign. So we take those out. We also included attributes here instead of a select star. We spelled all of those out. So let's execute that. And it just was almost instantaneous. In fact, it's less than a second. And notice the logical reads here, instead of being in the millions, it was 1,924. So we're seeing that just by not having an OR clause in the from and doing a star and doing the function, that we greatly improve the performance. Indexes are one of the major ways to improve performance as far as retrieving data in a database is concerned. And all DBMSs utilize indexes. In most, including SQL Server, there are clustered and unclustered indexes. So a clustered index is physically defining the order in which data is stored in a table. So records or rows that have very similar values on the column where the index is will be stored physically close. Now, there's only one clustered index per table, and if you think about it, that's about the only way you could do it, because you can't physically have things in multiple locations. So you put a row in a single location and cluster it on one column. Now, SQL Server gives a primary key constraint, an automatic clustered index. That's the default. You don't have to do it. You'll end up with an index on the primary key anyway, but you can have the primary key be unclustered and put your single clustered index on a different column. An unclustered index doesn't physically sort data inside of the table. Now, whereas there can only be one clustered index, there can be many unclustered indexes attached to a table. Remember that a table is physically sorted on the clustered index. In an unclustered index, it contains column values on which the index is created. When a query is submitted using an unclustered index, the index is examined to find the address of the row. When you find the address of the row, then you go to that address. So that's an extra step that's incurred in an unclustered index, which is why retrieval is faster using a clustered index. Now, if you have an unclustered index, that's nice. You only want to use them though when it's going to help you have faster speeds. Early on, I tended to index everything, and I found out that the inserts were so slow, and the fact that it consumed so much more space was also a problem. So our next step will be to build some unclustered and some clustered indexes on a table in SQL Server and see a couple of ways to do it. Let's look at how to create a non-clustered and a clustered index in SQL Server. The first way we'll do it is with SQL code, and then we will do it with the graphical user interface. So we create non-clustered index. We give it a name, and in this case it's stock data is the table, ticker symbol will be the attribute, and this is kind of a naming convention that you have in SQL Server. IDX, index, NC, non-clustered, table name, and attribute. It's on the stock data table using the ticker symbol. So our index is going to be on the ticker symbol attribute. So if we execute that, we see it's successfully completed. Now if we wanted to delete or to drop that index, we would highlight it and drop the index. So that's creating and then dropping the index. Let's look at the clustered index. And in fact, it's very similar. We create unique clustered index. The table's going to be stock data, and the attribute is going to be price ID. So I can create this clustered index on the price ID column. It means it has to be unique. And then to get rid of it, we do the drop index command. So let's create our indexes now with the graphical user interface. So I right click on the table name, I choose design, and I'm in table design. I right click in the white area and I go to indexes and keys, and I come down here to add. So I add a key. Now I'll choose which column that the index is going to be on. I will choose ticker symbol because this will be my not clustered index. I choose ticker symbol. The sort order is ascending. Rarely, but sometimes you might want to reorder it to descending for your index. I click OK. This line here where it says create as clustered, I need to make sure that that says no. If I wanted to change it, I would change it here. I click close. I come up and save my table, and it's saved. Now if I want to go look at it again, I'll go back to design, right click in the white, choose my indexes and keys, and there's my index. Now I'll delete it here, and now I'll make my new index, which is the clustered index on price ID. So I choose add. Price ID is already selected, but if it weren't, I could choose it here. And I want to make it clustered. So I will say yes. Close. I have to save my table. I'll close it. I'll re-examine it to make sure that it's there. So I right click, design, right click, choose indexes and keys, and there is my clustered index. Here are some additional performance tricks that will help us speed up our database. First, always put a prefix on the object names with either the owner or the schema. For example, put something like DBO in front of the table name stock data, and if it's not DBO, it could be your own username dot table name. Second, eliminate cursors from the query. We haven't covered cursors in this video, but cursors are very slow and they harken back to a programming from a long time ago that's more line by line. And SQL is set based, And wherever possible, set-based queries always perform better than cursor queries. So whenever possible, eliminate cursors. Third, avoid using a non-correlated scalar subquery. And a scalar subquery is a subquery that returns exactly one column value from a row. So looking at an example, I'm going to do the same query two different ways and look at the performance of each. The first, I have price ID, trade date, ticker symbol, closing price, and volume from stock data, where st close equals, and here's my scalar subquery. It's scalar because it's going to return a single value. Select max close from stock data. I've got some performance assessing components at the beginning and end. Now, looking at the way that's not scalar, and it actually looks a little more clunky and not as elegant. We declare a variable that's going to hold that closing price, and then we set that variable equal to the max of st close. So we calculate that one time here, and then in the main query, which is pretty much the same as the previous, except that there's no subquery under the where. And I have price ID, trade date, ticker symbol, closing price, volume, where the closing price is equal to at Van Halen. Now it presupposes that there's only going to be one price that is the largest, and looking through our pricing data, that's a good assumption to make. So here are the performance of those two queries that retrieve the exact same data. This version, again, has a scalar subquery, meaning a subquery after the where, and it is returning a single value. Now, a scalar subquery can also be in the select and the from, and you still have the same issues. Coming down here to look at some of the performance, we see CPU time 122 milliseconds, elapsed time 45 milliseconds. It's a pretty easy query for the system to calculate. And notice we have a scan count 14, logical reads 13,398. Let's compare that to the declare a variable version of the same query. See, we got the same answer. CPU time 78 milliseconds, elapsed time 10 milliseconds, so it's faster, half the number of logical reads. The scan count is also half. So in this particular instance, you can still see that there's a performance improvement by moving the scalar subquery into a variable. The last area of performance that I want to talk about relate to weight statistics. Now I'm just going to look at these briefly, but weight statistics can be examined at a much deeper level, and perhaps I'll do that here in a future video. But SQL Server records the length of a weight and the cause of a weight. And there's two dynamic management views that can be queried as if they were just tables. And they're going to give us aggregated weight statistics for all weight types and weight statistics for currently executing requests. So here are these two dynamic management views, and I just want to show what they look like and how to query those. So I will execute the first, which is aggregated weight statistics. And there's a lot of rows, but you get to see weight type, waiting tasks, wait times, the max wait times in milliseconds, the signal wait time in milliseconds. And there's all these locks, there's lots of different points where you can see there could be waiting. Second, we'll query just the waiting tasks. So we execute that, and there's far fewer rows here, and we get to see times and wait times and different reasons for those wait times. So let's explore the dynamic management views, and these two in particular, much deeper in a future video, but that's certainly one way that we can examine performance. There are a lot of ways to speed up a system, and ultimately we want faster queries, faster systems, and so we examined viewing indexes, how that could help us, some better query design. It's really good to understand your data, the nature of the data, and how the data is going to be used. Those are really important because that can affect some of the techniques that we use. And we also looked at dynamic management views. So all things being equal, faster is always better than slower.